Well, greetings, mathletes, and welcome back. Today we're going to take our first look at derivatives. Now, we've actually been doing derivatives. We've been playing around with this idea this whole time. What a derivative actually is the slope of a tangent line at a particular point on a function. Where we're going to be going with this, I mean, up until now, we've used the difference quotient to find these things. Whether it be an average rate of change over an interval or an instantaneous rate of change at a point. But what we're going to be doing today is finding ways to do this faster, being able to find a function that will tell us the slope at any point, which is honestly, if you keep having to find slopes on a particular curve over and over again, it's nicer to have a function you can just plug something into instead of recomputing the difference quotient every single time. Because that can get kind of messy. So we're going to start out by connecting the idea of the derivative to what we've been doing already, and we'll look at some new notation because new ideas, new notation. And then what we're going to do is start taking a look at some shortcuts to be able to get to these derivatives without having to go through the difference quotient every single time. Now, all of these rules do come out of the difference quotient, and when we take that limit of the difference quotient. So I'll show you where some of this stuff comes from, but mostly we're going to be focusing on how to use it. So in any case, let's go ahead and get started here. Okay, so up until this point, we've been looking at the limit of the difference quotient in terms of the, oh, that's not what I wanted to write. H approaches 0 of f of x plus h minus f of x over h, right? And up until this point, and I'm not writing it here because it's going to be hard to erase, x has been a point. It's been a number that we're dealing with. But if we want to find a general function that describes the slope for any point on f, we can just let x be a variable, right? We just don't put any value in for x, and we'll still take the limit as h approaches 0. What this ends up doing is it gives us the slope at any given point. So all you have to do when you get that expression is plug in whatever value you want for x, and you'll find the derivative at that point. It's the slope of the tangent line at that point. Now, notation. So if f is our function, the derivative would be written f prime, and that's how you say that. You say f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x over h, right? So it's the limit of the difference quotient. Now, there are different notations for the derivative, okay? They all have their place, but for the most part, they're pretty interchangeable. I'm going to put the two we're going to use the most first. So the other notation is ddx. You would say ddx of f of x is equal to all that, right? That's another notation. Another way to write the derivative is, let me make that look more like a d. Oh, I missed the eraser. Try that again. Would be df of x, right, where d is a differential operator. We don't really use that much in this semester. And then also you may see this, dx of f of x, right? So those are all different ways that the derivative is written. A lot of the time too, when your function is y, right, if you have y equals something, blah, 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 you'd write ddx of y, right? That's the same thing as y prime, which is very commonly used with variables. But also, this notation here is compacted, and you treat it very much like a fraction, actually. And you would write dy dx. Okay, so all of these notations are different ways of writing the derivative, and we're going to be using really not so much these two, right? they're not wrong. We just don't use them that much this semester because they actually get more in the way than they actually help. But this semester, these notations, the prime notation for a derivative and the ddx notation, and x just denotes what the independent variable is. So that just tells you what you're taking the derivative with respect to. So, and we'll talk about that another time when it comes to taking a derivative with respect to things. In any case, these are our notations. And so I want to go through and just show how this works. So let's do this to start. I'm just going to clear that off. And let's say we have a function f of x is equal to x squared, right? Now, we've done this before, but we've had values for x. So what we're going to try to find is f prime of x, right? So we need the difference quotient, and we need to take its limit. So we need the limit as h approaches 0 of, and I'm just going to go straight to it, x plus h squared minus, well, I don't even need those parentheses, minus x squared over h, right? So we're trying to get a hold of this. Well, notice, I don't have numbers here. I have x's here. If I square this out, I end up with, let's see here, that's going to be x squared plus 2xh plus h squared, and I just basically FOILed out that square, minus x squared over h. Now you notice this x squared minus x squared goes away, and so what I'm left with is the limit as h goes to 0 of 2xh plus h squared over h. And if I factor that h out there, I can cancel that down, right? Because I have an h in each term, I can pull an h out and kill the denominator. This ends up being the limit as h goes to 0 of 2x plus h, which just comes out to 2x. Okay, so what does that mean? Right? I mean, great, we found 2x. What do we do with it? Well, this is what that tells us. Since this is our original function, and we just found out that f prime of x is 2x, right? These two pieces of information here. Well, when we actually graph a parabola, right? Basically what this is telling me, if you pick an x value, like let's say I pick 2, and I want to know what the slope is right here at 2. All I have to do is look at f prime of 2, right? That ends up being 4 as soon as I plug that in. So that means this tangent line right here has a slope of 4. So that's actually what it's telling me. If I want to know the slope of the tangent at another point, like, I don't know, let's just pick -3. Let's say I wanted the slope at -3. Well, f prime of -3 is -6. And it turns out that the slope right here at this point, m equals -6. And so basically this gives us a convenient way to map out the slope of an entire function at every single point. What is interesting about this is that a lot of the time we end up knowing something about the way something changes, but we actually don't know anything about the function itself, and so we have to work backwards from that. And so understanding both directions is actually the point of this almost this entire semester. Basically, we're trying to figure out how to get to the slope and then how to get back from the slope. But those things look very different. Okay, so that's basically the idea. You just use the difference quotient, but you leave x as a variable. Okay, so let's look at another one. I want to use an alternate definition of the difference quotient on this one, and then this will be the last. This will be the last one that we work out using the difference quotient. So let's say this time I have y equals the square root of x, and I'm looking for dy dx. Remember again, That's the derivative of y with respect to x. That's how we would say that. So dy dx would be the limit. Oh, actually, let me give you the different definition. Here's another definition of f prime of x. This is the limit, and this time it's going to look more like a slope of f of z minus f of x over z minus x. Now you notice that z is just another x value, right? But this is as z approaches x. That's actually what we're looking for. We're looking for the limit as z approaches x. Now, so we're going to use that definition to come up with the derivative this time. So that would be the square root of z minus the square root of x over z minus x. Now I'm going to show you a little trick here. It turns out, really the dirty little secret that from algebra is that everything factors, right? If you just know what you're doing, if you don't limit yourself to whole numbers, everything factors. So even this z minus x can be factored. And I'm going to use this formula. Excuse me, that a squared minus b squared is equal to the square, excuse me, not square root, I'm thinking ahead, is equal to a plus b times a minus b. What that means is whatever's here and here, I can just take their square roots to get these numbers. And so I'm going to do that here with the z minus x. So this is now the limit as z approaches x of the square root of z minus the square root of x. But in the denominator, I'm going to factor this thing out. And you can always multiply it to convince yourself. It'd be the square root of z minus the square root of x times the square root of z plus the square root of x. Right? Well, right there, I can see that this cancels with this to make this numerator a 1. So now I'm looking at this. The limit as z approaches x of 1 over the square root of z plus the square root of x. Well, if z is approaching x, and I don't have any problems, this is basically the same. This would end up being 1 over the square root of x plus the square root of x, which is 1 over 2 times the square root of x. And it turns out that is the derivative. This will give you the slope at any point. And if we think about the square root, right, dy dx is going to be 1 over 2 times the square root. Basically, if I do, I'm just going to do a quick graph here. What that means is I can find the slope at any point on a square root function now. So if I plug in the point 4 right here, the square root of 4 is, this would be 1 over 2 times the square root of 4, and that gives me 1/4, right? So here the slope is 1/4. What's interesting about this now, in fact, let me just get that part off there so I can draw, is it makes sense why there's no, it makes algebraic sense now why there's no derivative here at 0, right? First of all, it's a vertical line, right? If you drew a tangent line there, it's vertical, which has an infinite slope. And you look at what happens here, if I plug in 0 for x, I get 1 over 0. And that's, well, 1 over 0, right? If you took a limit, it would go to infinity. So, you know, that gives you an undefined slope right there. So you can actually see that it's undefined just by plugging in the x value, even when you don't even know what the function looks like. So that's the value of these things, right? You can come up with a function that will give you the slope at every single point. Now, we want to take a look at some ways to shortcut this process, because taking these limits every time is actually quite painful. I know I don't particularly enjoy it. I think there's some beauty in it, but you know, once you've done something a few times and you got the idea, it's nicer to get to the point. So, rules of derivatives. Okay. Now, when I'm describing the rules, it's actually easier to use the DDX notation, but not for everything. So I'm going to be mixing up the notations a little bit depending on what makes sense. So first of all, assume that f of x and g of x have derivatives, right? Not everything has a derivative. So assume these functions do have derivatives as we're going. So first of all, there's rules for a constant function, and c is a constant. If I take the derivative of a constant, I get 0. That makes total sense. A constant function is horizontal. What's the slope? The slope is 0. Well, there you go. Now I have the slope at every point. It's 0. 2. There's an addition rule, which says that if I take a derivative of a sum of functions, and basically like a polynomial is a sum of a bunch of little individual monomial functions, I can actually just take the derivative of both of these separately. Right? Or if you want, you can just write f prime plus g prime. Right? That means the same thing. Okay. So if I have more than one term, basically what that means is I can take the derivative of each term separately. You can also pull a constant through a derivative. So if I'm taking a derivative of something like this, c times the function f of x, I can just take c and multiply it by f prime, right? I can just take the derivative of the function by itself and leave the constant alone. That's actually a really useful trick. Let's see here. 4 is the power rule. Now, the power rule, you can actually get the power rule from the sum rule just by applying it over and over and over again. Oh, excuse me, I said that backwards. I haven't gotten to I was going to say the product rule, but we haven't talked about the product rule yet. Yeah, so the power rule basically says that if I'm taking a derivative of something with an exponent, right, that what I do is I multiply that exponent on the outside and then reduce the exponent by 1. Now, that's interesting. I'm just going to apply this real fast. We just did x squared, okay? We used the difference quotient from it. I just want to point out what happens if I do this and use the power rule. So the power rule says you take the exponent and write it out in front and then reduce the exponent by 1. Right, so that'd be 2 to the first, which means that this is 2x, which is exactly what we found before. Right, when we found the derivative of x squared using the difference quotient, we got 2x. This power rule shortens that business quite a bit, so that's kind of nice. All right, I want to point out too that this power rule will also handle the square root. Right, if I take, in fact, let me switch colors just so it stands out a little more. So let's say I'm taking ddx of the square root of x. Well, the square root of x is the same thing as x to the 1/2. Now it's an exponent. Right? So it's really convenient. This is why you actually had to learn that back in algebra, why you could switch roots and exponents like this. It's a very useful thing in calculus. In fact, it is so much easier to deal with exponents than roots in calculus. Now we can apply the power rule, right? Because this is a power function, so that means that I take the exponent and put it out front, and I'm going to multiply that by x, and then I'm going to reduce the power by 1. Now it's at 1/2. If I take 1/2 and subtract 1, I get negative 1/2. Okay. Now, that's a correct answer, but we typically don't use negative exponents in our final answer, and we usually rewrite things back in the form we got them in. So since I started with a root, it's appropriate to end with a root as well. So the negative exponent means that this is now 1 over 2x to the 1/2. And now this is x to the 1/2, so that means it's a square root. And you notice we get the exact same expression that we got from the difference quotient. 1 over 2 times the square root of x. And we used a rule for powers here. So that's kind of a cool deal. It gets us forgive the pun, but it makes it a very powerful rule. This, and then the last two rules that we're going to look at are the product rule and the quotient rule. And I will point out that if you just use a negative exponent, then the quotient rule is actually just the power rule again. So you can, anything that you use the quotient rule, you could use the power rule on. So let's go ahead and look at those last two. And then basically after we get through these last couple rules, it's just going to be examples from here on out of how to use those rules in concert. So, okay, so product rule. The product rule, basically, it's what do you do when you have two functions multiplied by each other? So it's d dx of f of x times g of x. Okay, so this is how it plays out. Now there's the rules ends up being written in different forms, in different orders, because there's addition in there, so you can swap things around. But it's basically the first function times the derivative of the second function plus the second function times the derivative of the first function. And so this is how I remember it. And you're welcome to use any memory device you want. I just refer to this function as 1 and this one as 2. And I remember it as 1d2 plus 2d1. Right? 1d2 plus 2d1. So, I don't know. I don't have anything better than that. But it works for me. Basically, you're going to take the derivatives of both of them and then multiply a derivative by a function and add those together. I mean, that's basically what you're looking at. Okay, so 1d2 plus 2d1. And then the quotient rule, oops, I want to switch back to blue. The quotient rule says that if I have f of x divided by g of x, right, I'm doing a ddx of that. Let's go ahead and get this off of here. It's going to look similar to the product rule for a moment, but it does look a little different. So that would be g times f prime minus f times g prime. So you notice the negative first, and it is over the square of whatever g of x is. Right? So this is how I remember it. This is how my calculus teacher told it to me. If I look at the functions this way as low over high. Oh my God, I can't believe I wrote that backwards. Okay, let's try this again. High over low. I don't know why I put low over high. Right, so f is on top, g's on bottom. The way I look at it is it's low d high minus high d low over the square of what's below. Right, that's how I remember it. It's low d high minus high d low over the square of what's below. Right, I feel like it's the beginning of a limerick or something, but I've never bothered to try to complete it. And nonetheless, these rules, really the only ones you're going to end up memorizing where you're like reciting things are probably the product rule and the quotient rule. So those are the two that you really want to focus on, because you don't want to lose those. You have to be able to do it by reflex. The other ones, once you do a few of them, it really it becomes very clear pretty quickly what you're supposed to do when. Okay, so we're going to take a look at a few examples now. We have all this stuff that we just learned will work as rules. Let's see how it plays out. Okay, and as we go through these examples, I'm going to be mixing up the notation a bit just because I want you to get used to all the different notations. They really are interchangeable. It's just that there's certain situations where one notation is a little less clunky than the other notation. So you just move back and forth through them fairly fluidly. So let's go ahead and start with our first example here. Let's say we have y equals 3x squared minus 4x plus 1. Okay, and what we're looking for is y prime. Now, these are actually one of the most convenient polynomials are real nice to take derivatives of because it's all the power rule. We know from the addition rule that I can take derivatives of each term separately. I know that I can ignore the constant and multiply it back in afterwards. So I'm actually going to do the extra work on this on the first term here. Well, actually, I'll do it on the whole problem, and we'll just go from there. So first of all, I know if I'm going to take y prime, I can take and pull the 3 out and just look at d dx of x squared. I can do the same thing with the 4. Pull it out and just take d dx of x. And then 1 is 1. I'm going to take d dx of 1. Well, if I look at what this does, right, the derivative of x squared is 2x, and I would multiply the 3 back in, so that gives me 6x. Over here, well, when I take the derivative of just an x by itself, the exponent is already a 1, so 1 comes down in front, and then the 1 turns into a 0 because we dropped the exponent by 1. Just like here, the 2 turned into a 1. Here, the 1's going to turn into a 0. And so x to the 0 is 1, so this just ends up being minus 4. Now, you do want to be careful with the constants, because technically 1 is equal to x to the 0, but the power rule, this is the only place the power rule doesn't work, right? When I'm taking the derivative of x to the n cannot equal 0. Okay, so it doesn't work for that one. We already know that the derivative of a constant is 0. So this is now plus 0. We usually just don't even write that. So what we end up with is 6x minus 4, right? Now, I want to point out that I put in all the little details so you can see what you're taking the derivative of. In practicality, what happens is you just do it all in your head, right? The 2 gets multiplied by the 3 to make a 6, and then I reduce 2 by 1. That's a 1. 1 gets multiplied by the minus 4, and I reduce 1 by 1, which makes it x to the 0. And then 1 is 0, right? And so you just do it all in your head, all in one step is what you usually do. And I can see from here that that's 6x minus 4. You'll get to the point where you don't even bother writing the x to the 0. You may be at that point already even before we start. I don't know. Write in what you need to keep track of everything until you don't need to write it in anymore. Because otherwise, you're going to end up filling your whole paper with all kinds of stuff just to do something that may otherwise be relatively simple. But if you need the extra steps, put them in until you don't need them anymore. Okay, so let's go ahead and look at the next example. So let's say I have f of x is equal to x plus the square root of x. Okay, so we're looking at that now. Well, again, we have 2 terms, and actually, I want to find f prime. right? So I can actually do the first term fairly quickly. It has a 1. The derivative of x is just going to be 1, right? Because anytime you have what's called a linear term, meaning the exponent on x is a 1, the derivative of a linear term is just its coefficient. Okay, now we have this square root of x. So I need to figure out how that's going to work. So let's rewrite that as x to the 1/2. I'm going to do it on the side here. And so that means that the 1/2 comes out in front. And if I subtract 1 from 1/2, I get negative 1/2. Okay, so I have that. Now I just need to deal with the negative 1/2. So negative means it's on the bottom. And the 1/2 means it's a square root. Okay, so this is now 1 plus 1 over 2 root x. And so we just found our derivative. Right? Now we can take and find the slope of this function at any point we want. And we can even see where it's where we're going to have an undefined slope as well. Because if x is 0, we're going to have a problem. Right? Okay. So let's look at another one here. All right. So let's say that y is equal to 3 over z squared plus 5 over z cubed. Yikes. Well, that looks kind of scary, right? Just at the onset. Here's what I want you to do. We've actually used all the tools so far that you would need for this, right? This can be handled using the power rule. Pause it right here and see if you can figure out how the power rule applies to this, and then we'll work it out together. But pause it right here and see what you can get. Okay, so I'm assuming you've paused it and you've worked on it. Hopefully what you found, and by the way, you are looking for y prime. I assumed that. We can rewrite this as 3 times z to the negative 2 plus 5 times z to the negative 3. And so we can see what happens from here now. So let's see here. If I bring the negative 2 down and multiply it by the 3, that makes it a negative 6. Okay, this is where you have to be careful because this is a negative exponent. And if I subtract 1 from a negative, it makes it more negative. So if I subtract 1 from negative 2, it makes it negative 3. So that looks like that. So I know my first term is negative 6 z to the negative 3rd. Let's make that a little more 3-ish. All right, and then over here, negative 3 times 5 is minus 15, and then I'm going to subtract 1 from negative 3, which makes it negative 4. So it's minus 15 z to the negative 4th. Now, I do want to say there's nothing wrong with having negative exponents in your answer. However, there is a convention, especially when there's no context, right? There's no like word problem we're working on or anything like that. The convention is to put things back in the form of the original function. And you notice the original function doesn't have negative exponents. It just puts the variable in the bottom to make the exponents positive. And so we're going to do the same thing. So this would be negative 6 over z to the 3rd minus 15 over z to the 4th. Right? And that's just manipulating it via algebra. Now, this is one of those things that you do have to watch out for on exams because sometimes our software marks things wrong that are absolutely correct. I consider that a correct answer as much as I consider this a correct answer, but your homework software may not. So be able to move back and forth between the two forms, right? That's going to be important. All right. So let's take it a little bit further here. And then I'm going to, after I finish these examples, I'm going to talk about some of the exceptions, things where there's going to be problems. So, yeah. There we go. All right. So let's take a look at another one here. How about if I have y equals Oh, let's pick out something. Let's do it this way. 2x plus 3 times x squared plus 4x plus 5. Okay, so you have two choices here, right? You could multiply the whole thing out and just treat it like a polynomial, right? There's no problem there. But the other thing we could do, and I'm going to do it this way so I can demonstrate the property, is I'm going to use the product rule because this is multiplication, and these are two functions. I'm going to call this f of x, and this is g of x. And if I think about this as my one function, this is my two function, right? I got 1d2 plus 2d1. So that means I'm going to have f times f of x times g prime of x plus g of x times f prime of x. Right? Both of the, and so you notice I still have to find g prime and f prime. So let's go ahead and do that first. So this is f, this is g. So just looking at this, f prime of x is going to be, well, let's just take the derivative of this first term, or this first factor. Derivative of 2x is 2. The derivative of 3 is 0, so I'm done there. Now looking at g of x, we want g prime. So the first term is going to be 2x, the second term is 4, and the derivative of 5 is 0. Okay, so now we have these two pieces. So we're just going to put them together. So f is 2x plus 3, right, times g prime. G prime is 2x plus 4. Okay, and then I'm going to add that to, let's see, g. G is that, oh, I should have given myself more room. Let me do this. We'll put it out here. So let's see here. F was 2x plus 3. G prime, where'd it go? There it is, was 2x plus 4. And then it's going to be plus, let's see, we need g. G is that big thing. X squared plus 4x plus 5 times f prime. And f prime was 2. So all we have to do now is multiply everybody out and collect our like terms. Okay, so if I multiply this out, this is going to be 4x squared. See, my middle terms will be 6x and 8x, so that's plus 14x. And the last term is plus 12. And then over here, I have plus 2x squared plus 8x plus 10. So now, y prime is just a collection of all these like terms. So that's going to give me 6x squared. Right? That's from this term and this term. 14 plus 8 would be 22. So that's plus 22x. So I use that and that. And then that's a 10. 12 plus 10 is also 22. Right? And now I have the derivative. And so what I did was I used the product rule for this. Now, I'm not sure if it would be more work to multiply out this first and use the polynomial rule, or whether it's faster to do it this way. It's probably more to keep track of using the product rule, but that's just because you're new to using the product rule. It's you just need practice using it. At some point, it's going to get to the point where you can just write it down as you go. So you'll say, oh, I'll take the first function, you write it down, and then you take the derivative of the second function as you're going. In fact, yeah, that's just one of those things that experience is what makes you quicker at it. So, all right. So now, let's take a look at another one. Let's say I have, let's say y is equal to 3x to the fourth over x plus 1. Okay, so we have a quotient here. Now, I do want to point out, you could always rewrite a quotient as a product, right? I could rewrite this as x plus 1 to the negative 1, right? And if I did that, and so this would be f, this would be g, I could go through and use that product rule and have no problems. I'll come up with the correct answer. But we have a quotient rule. And remember, the quotient rule is, well, it works better with, I always remember it this way: low D high minus high D low over the square of what's below. Okay, so this will be our low, this will be our high. That's a hoe. Let's try that again. I know that's the wrong spelling of high, but I needed something to be short. Okay, so I need, if we're going to use the quotient rule, I need low, which is x plus 1, times the derivative of the top. The derivative of the top, and you notice I'm just doing this as we go this time, is going to be 12x to the third. Okay, so that's low D high. So that's for this part. Minus high, which is 3x to the fourth, D low. Now, if I take the derivative of the denominator, derivative of 1 is 0, derivative of x is 1. So that's just times 1 over the square of what's below. Okay, now it's just a matter of simplifying. So if I multiply this part out, oh, this wrote the equals in the wrong spot. There we go. All right. Now, if I go ahead and distribute this out, I end up with 12x to the fourth plus 12x to the third minus 3x to the fourth over x plus 1 squared. So collecting my like terms gives me 9x to the fourth plus 12x to the third over x plus 1 squared. Now, you could square out that x plus 1 to get x squared plus 2x plus 1 or what have you. There's actually no reason to have to do that this time. Right? You could multiply it out if you want, unless there's a reason to, like you're going to be able to eliminate a factor or something like that. Then there's no point in doing it. Nonetheless, this would be our y prime. This is our dy dx. This is our derivative. Okay. Now, most of what your homework is going to be is just going through and practicing this stuff. And so there's going to be little things here where there are things that maybe you didn't think of, or little tricks that don't seem like they should work right here, but they end up working. Again, experience and working through some of those tough little things are what you need to be paying attention to. Experience is what gives you fluidity with this. Okay, so so properties of derivatives. Okay, so one, if a derivative exists, right, f prime of x at x, right, so some point x. So if the derivative exists at a point, then the original function f of x is continuous at x. So whatever point, if you can take a derivative at a particular point, if that derivative is not undefined, then that means the function is continuous at that point. Now, just because a function doesn't have a derivative does not necessarily mean, excuse me, just because a function is not continuous at, am I saying that wrong? Okay, I am. Just because a function is continuous does not necessarily mean it has a derivative, though, right? If the derivative exists, then the function is continuous there. Just because a function is continuous does not mean that a derivative exists. Here's an example, right? If I have a function that does something like this, right? Remember that the derivative is actually the limit of the difference quotient. If I'm trying to find a derivative right here at this point, at this x, if I do it from the right-hand side, right, I end up with these lines, and I end up with a particular slope. If I do it from here, you notice these are different slopes. If they don't come to the same number, then your derivative doesn't exist. So almost anywhere, this is called a cusp. If your function has a cusp, it doesn't have a derivative at that cusp, right? And that's an example of something that's continuous it's something that's continuous that does not have a derivative at that point, right? The function value exists, but the slope does not. So, those are things that you're going to have to watch out for. Let's see here. Let's go ahead and get rid of that. Okay, so that's the main property that I want you to be thinking about. There's also some other notations. For example, if you take a derivative of a derivative, right? So if f is a function, f prime is the first derivative, right? Or d dx of f. F double prime is the second derivative. We would write that d squared dx squared of f. And that's that is the change in the change of slope, if that makes sense, or the change in the change of f. You could also go up to a triple derivative. If you go past 3, generally what you do is you just put a number in parentheses as in an exponent spot. Excuse me. And then let's see here. What were some of the other ones? Those are the main ones that we're going to be dealing with. And then the other thing, I'm just going to point this out because this has come up. The position function for a free-falling body on Earth, well, actually on any planet, looks like this. In fact, I'll just leave it as f of x. If I take that derivative, what I'm finding is the velocity, right? Because the rate of change in position is a velocity. We've actually talked a little bit about that already. If I take the derivative, look what happens here. I have 2 times a, so I have 2a, and then x, and so it'll just be x because the exponent's 1 now, plus b. That's kind of interesting. And then the second derivative is the change in velocity. So that's the derivative of velocity. Turns out that is acceleration. And if I take one more derivative, what I end up with is 2a. Right? So we can actually, and remember, a is just a number. And really where a lot of physics comes in is starting here, because that's the thing you can measure, right, is what the acceleration due to gravity is, and working your way backwards, back up the ladder to the position function. So those are actually kind of fun little exercises. This is just one of the applications that's coming, so I'm going to be talking to you about it. I know in the discussion board I saw at least one person try to use this, even though we didn't have it as a tool yet. But that means that you're aware of it, so that's good. All right. So that's everything I wanted to talk about today. And I know I probably rambled a little bit at the end there, but that's okay. I pretty much always do that anyways. So until next time, keep your pencils and your wits sharp.